Alright, AP Physics 1, this is our final lesson on Unit 3, Forces and Newton's Laws. And today we're going to be specifically analyzing connected objects, objects that are physically connected to one another. Now, the best way to learn about how to analyze systems of connected objects, and by that we mean objects that are literally connected to one another, is really just to go through an example. So let's have a little scenario here that you're probably all familiar with, which is a game of tug-of-war. Let's say Team 1, the team on the left, has a total mass of 150 kilograms, and Team 2, the team on the right, has a total mass of 600 kilograms, because obviously they've been taking steroids or something to get their mass up. The coefficient of kinetic friction between each team's shoes and the ground is 0.5, and we can probably guess that Team 2 is winning, because they're cheaters and using steroids, and if they're winning, what will the acceleration of each team be? So when we're analyzing the system of what we call connected objects, these objects have to be physically connected to one another. And in this particular situation, it's easy to see how they're connected by the rope. So however Team 1 moves, Team 2 is going to have to move the same way because they are physically stuck together. Now, there's a couple of different ways we can use to analyze these systems. We're going to go through them both to talk about which one that you prefer, but the first one we're going to go through first is the system of equations method. And we start off doing this by going ahead and drawing an FBD for each team. And when I do that, went ahead and did it here. We have for Team 1 and Team 2, they both have gravitational forces. Now, Team 2 probably has a bigger, well, I know for a fact there's a bigger gravitational force because their mass is bigger. And those are balanced out by two normal forces. So Team 1 is the normal force going up, Team 2 is the normal force going up. We know that there is a tension force on each team. Team 2 is being pulled to the left by Team 1 with the rope. Team 2 is pulling Team 1 to the right by the rope. And we also know that there is a friction force between each team and the ground. Team 2 is using that friction force to push themselves to the right, to accelerate this whole system to the right. And Team 1 is planting their feet on the ground and being slid to the left. Their friction force is not enough to overcome this tension force. So overall, we know that the net force is going to be to the right. The acceleration is also going to be to the right. So let's go ahead and write net force equations for each team. Oh, and before we even do that, let's go ahead and define the direction of acceleration as being positive. Now that's really important because we're going to see later it's going to simplify our math. So let's say to the right, this is a positive direction for both teams, and we can go ahead and say that up is positive, that it really shouldn't matter too much. For Team 1, we write our net force equations. Well, on the x, it's going to be tension plus friction is equal to the mass times acceleration. But notice, this is all for Team 1. So I put a 1 on every single piece. I don't want to get them mixed up with Team 2. And then in the y direction, their normal force and their gravitational force will equal to 0. They're not accelerating vertically, they're only accelerating horizontally. So Newton's second law in the x direction, Newton's first law in the y direction. And then for Team 2, it's going to look really similar. I'm going to have friction and tension once again in the x direction. They're accelerating in the x direction, all with 2's. And then in the y direction, their normal and gravitational force are going to be balanced on Newton's first law. So be real careful. The equations look almost the same, but we have 1's and 2's to keep them separate from each other. So I've gone ahead right here and just redrawn the FBDs with the axes. I've gone ahead and written all the constants that were given to us in the problem, so the masses and the coefficient of friction, and I've rewritten the net force equation. So at this point, let's go ahead and solve for some forces that we definitely know. Well, first we can find the Fg for each team, because the Fg is just their mass times the acceleration due to gravity, which is 10 meters per second squared. So for Team 1, that's 1,500 newtons down, because they had a mass of 150 kilograms. For Team 2, that is 6,000 newtons down. And additionally, if we look at our net y equations, that tells us that since the normal force and the gravitational force have to equal 0 for each team, well, we automatically know the size of the normal forces. That for the first team, it will be 1,500 newtons up. For the second team, it will be 6,000 newtons up. And additionally, well, we can actually solve for the friction forces too, because remember the friction force, particularly for the kinetic friction, is just mu k times Fn. So the coefficient, which is 0.5 times the normal forces, so I stick it in for each of team. For Team 1, we get 750 newtons of friction to the left. For Team 2, we get 3,000 newtons of friction to the right. Up to this point, we've actually really just been doing prep for finishing this method of system of equations. So, once again, everything here is no different. All I've done now is I've written the forces we've calculated over here on the right-hand side, so I just have them for later. And what we're going to do now is we are going to specifically look at the two equations that involve acceleration, which would be this equation here and this one here for Team 1 and Team 2. And I'm going to rewrite them down here. Just nothing done, I've just literally copied them. But I went ahead and did one on top of the other. We'll see why that is in a second. And there's a few things we want to notice. One, previously I wrote the force of tension on Team 1 and the force of tension on Team 2, but those are a force pair, so we know that those forces of tension should be identical. So I can go ahead and get rid of the 1 and the 2. It's just now Ft and Ft. Additionally, and this is going to be a little bit more of a jump for some of you, the acceleration of each team must be the same in order for them to be connected. Now, why exactly is this the case? Well, let's say that Team 2, the team that's winning, was accelerating faster than Team 1. Well, if they're doing that, they're going to pull on the rope, and in such a way, the rope is literally going to snap. Because Team 1 is moving faster away than Team 2, well, that rope has a set length. It can't go, it can't stretch, so it literally would just snap in two. So that cannot be the case. Additionally, we know that Team 2's acceleration can't be bigger than Team 1, or while Team 1 is pulling, Team 2 would literally just slide into them. So we're looking at scenarios when that length of rope between them stays constant. It's not going to change. So we know the acceleration on Team 1 equals the acceleration on Team 2, just equals the acceleration in general. I can get rid of all the 1s and 2s on all of my accelerations. Lastly, we're going to go ahead and take one further step that I typically don't like to do until we plug in numbers. But for this particular method, it is going to help out. And that's where we're going to go ahead and specifically define directions for the different forces at play. So if I look at Team 1, well, tension is positive, friction is negative, normal force is positive, Fg is negative. So I'm going to go ahead and write over here that this is positive, and that should be negative. This is negative, that will be positive. And for Team 2, I get positive, negative, positive, negative. So I'm going to go ahead and say friction is positive, but tension is negative. Fg is negative, Fn is positive. And we're going to see why that is in just a second. But now I've gone ahead and I've adjusted that here too. So I meant because I made F1 negative, okay, and I've made Ft negative. All right, all good. So now that we've adjusted those signs, what we actually have is a system of equations. So I've got equation 1 here and equation 2 here, and they make a system because I just have them, but how do I know I can solve them? Well, I actually only have two unknowns. I have Ft I don't know, and I don't know the accelerations, but I know the masses, and I know FF1 and FF2, so I have two equations, two unknowns. I can definitely solve that by combining these equations in the system together. So I'm literally going to write this up like an addition problem, where I put one over the other, and I'm going to add the left sides of my equations and then the right sides of my equations, because that should be totally allowed. If I have some left part and some right part where they're equal, and I have another left and right part that are equal, if I combine all the lefts, that should be equal to the combined version of all the rights. There's nothing weird happening there. So if I do that, let me start adding these pieces together, and what we'll see is that Ft and minus Ft, well, if we add those together, they're going to go away. And I'm left with FF2 minus FF1 is equal to M1A plus M2A, and if I want to take that even a step further, I can pull M1 and M2 away from the A, so I get this final equation here, FF2 minus FF1 equals M1 plus M2 times A. So, now I have this equation I literally just made from that system of equations, FF2 minus FF1 equals M1 plus M2 times A, and I can go ahead and rearrange it. I'm going to rearrange it to solve for A, which, okay, I know it's been a while, but that's what we were looking for. We were looking for the acceleration of each team, which we know has to be identical, but we still want to find the number. How quickly are they accelerating? So I can plug in FF2, FF1, M1, and M2. We do that, 3,000 newtons minus 750 over 150 kilograms plus 600, and we get 3 meters per second squared to the right. That will be the acceleration of these teams. So we've now solved this problem using the system of equations method. But I think it's fair to say that there were a lot of steps in that method, so let's kind of list them all now, and then we can practice it again in a minute. 1. You want to draw an FBD and write net force equations for each object that is going to be accelerating, that you want to consider in the problem. We want to define the direction of the acceleration as the positive direction. That will always make our math come out way, way easier. And additionally, let's go ahead and alter the equation so that if you have a force in the negative direction, you go ahead and label it as negative, even though I don't typically like to do that. We're going to identify any givens that we have in the problem and easily calculate info. So for instance, if you have masses, you can quickly figure out the gravitational forces. If they're on nice level surfaces, you can figure out the normal forces. If you're given a coefficient, you can figure out the friction forces, etc. We're then going to form a system of equations from the two net force equations that involve acceleration, such that we can eliminate a force pair. So one of the unknowns will go away. And then we're going to just solve for the desired unknown. And lastly, we can double check our answer with the net force equations. Now, you might be thinking, but Mr. Varvier, we didn't do that. So let's do it right now. So once again, FBDs, givens, forces I calculate, my net force equations, and now we know the acceleration is 3 meters per second squared to the right. We just calculated that. So what I want to do, now notice, I went ahead and reverted my net force equations back to their original form, so without any of the changed positives and negatives, so I could double check this all. So I'm going to go ahead and take the first one, and I'm going to solve for what I had gotten rid of, which was ft. That was why I canceled out of the system of equations. Let's make sure that that ft comes out right. So I'm going to rearrange it to get m1a minus ff1. I plug in the numbers that I have for these values, and I get a tension force of 1200 newtons to the right. Now let's go ahead and look at this other net force equation and rearrange it for ft, so it's going to be m2a minus ff2. I use the mass and the friction force I found and the acceleration I found, and you end up getting negative 1200 newtons, so 1200 newtons to the left for team 2. Well, perfect, that worked out because those numbers should be the same. They are a force pair, so one tension has to equal the other in the opposite direction. Additionally, another way I know that I did this correctly is if I look at team 1, well, the tension force better be bigger than the friction force or else they're not going to accelerate to the right. And that is in fact the case because the tension was 1200, the friction was only 750. And if I look at team 2, their friction force must be bigger than the tension force because they're also accelerating to the right. And if we look, that is indeed the case because their tension was 1200, but their friction was 3000. All right, well, that's all well and good. We use the first method, the system of equations, to solve for the acceleration of the teams. But there is another method we can use, and many of you are probably going to prefer it. So let's go ahead and discuss that now, and that method is known as Newton's second law for systems. Well, first thing I'm going to do is I'm going to go ahead and draw a system schema for the two teams in the Earth and draw the FBDs. These FBDs are exactly like the ones we had earlier, and most of you can make a system schema pretty quickly anymore. But what is Newton's second law for systems? Okay, so I've actually rewritten Newton's second law here, and I've just replaced all of the words that are different in this purpley pink color. If the forces on a system are unbalanced rather than an object, the system will accelerate with an acceleration directly proportional to the net external force acting on the system and inversely proportional to the system's inertial mass. Most of this makes sense. Instead of using the word object, we've used the word system, including the mass of the system rather than the mass of the object. But this part in particular is going to be a little new. It is the net external force acting on the system. So if I want to write this out mathematically, I would say the acceleration of the system in meters per second squared is equal to the net external force in newtons over the mass of the system in kilograms. But what exactly is an external and an internal force? If we had an external, you can probably guess we have internal forces too. Well, internal forces are when we have both objects and a force pair, and they are part of the system that we're looking at. So if I look at an entire system, there's only one part I care about. If there is a force between the objects and the part I care about, that would be an internal force. An external force is there's only one object in the force pair that is involved with the system, the part of the system that I care about. If the other object is outside, we often call this an outside force. Then it's going to be external, and we're going to see how those differ and more in a second. So once again, I went ahead and rewrote my system schema and my FBDs here, and now let's use Newton's second law for systems. So the first thing we need to do is we need to figure out, looking at this entire system schema and the FBD, what exactly is internal and external. So I'm going to look specifically at this region just because I only care about Team 1 and Team 2. I don't care about the Earth's motion. I only care about the acceleration of Team 1 and Team 2. And so if I do that, I went ahead and draw my dashed line here. I went ahead and draw my dashed line around the dots. And we see that the only, what we will call internal force, is the tension force. And the reason why that's internal is because, well, however much Team 2 pulls, Team 1 pulls the same amount back. So that force cannot affect their acceleration as a system because it cancels out within the system. Same thing over here, just once ahead, cross those out because I don't want to consider them. And that means all the other forces here are external forces because they're between each team and the Earth, and we don't care about the Earth's acceleration, only the teams. So those would be both gravitational forces, both normal forces, both friction forces. So what we could do now is let's go ahead and write out Newton's second law for systems, that the acceleration of the system is equal to the net external force over the mass of the system. And let's write out every single external force. That's Fg1 plus Fn1 plus Ff1 plus Fg2 plus Fn2 plus Ff2. And on the bottom, the mass of the system will be mass 1 plus mass 2. But what we notice at this point is that if I define, once again, acceleration as being a positive direction, so to the right, well, if I look, my Fn and my Fg's, those are going to cancel, and they're going to cancel here too, right? Because it's balanced in the vertical direction. So I can get rid of Fg1, Fn1, I can get rid of Fg2, Fn2, and I am just left with Ff1 plus Ff2 over M1 plus M2. I plug in my numbers, negative 750, because remember we have to pay attention to positive and negatives, negative 750 plus 3,000 over 150 plus 600. You stick that in your calculator, I get the exact same answer. 3 meters per second squared to the right. The exact same answer. So for Newton's second law for systems, let's go through the steps again. 1, we're going to draw a system schema and an FBD for each object in the particular part of the system that you're considering. We're going to highlight that part of the system schema and then determine which forces are internal and which are external. And once again, let's go ahead and define the direction of the acceleration as positive, just to be consistent. Going to identify the givens and easily calculated info, so any forces we can immediately calculate. We're going to write out Newton's second law for systems and insert all of the external forces on the masses. But then we're going to cancel out any balanced external forces and then just solve what's left of the equation for the desired piece that we want. So we've now gone through 2 different methods of solving problems that involve these connected objects. One being a system of equations, one being Newton's second law for systems. And they both have their pros and cons. So let's kind of go through those for a second. First off with the pros. The system of equations requires less conceptual understanding of the system. You're really just adding up, making these 2 equations, and you're crossing things out. If you feel really confident in your calculations but less in the conceptual part, this might be the one you want to consider. You can also easily double check your results because I can easily plug numbers back in and make sure everything works out. For method 2, Newton's second law for systems, this takes significantly less time, and you even saw that just a second ago. And honestly, it's mathematically simpler. You're really not a whole lot. You're not combining equations. We just have a single equation and getting rid of some pieces. But both of these methods also have cons. For the system of equations, flip side from the other one, takes a lot more time. So if you're crunched for time, you're going to might be in a little bit of trouble. And it's also very easy to mix up your positive and negative signs and make sure everything comes out correctly. But for Newton's second law for systems, it requires a much more careful analysis of the entire system. If you miss one external force, you're in trouble. So you have to make sure you have a real good conceptual grasp of everything involved there. And it's also a little more abstract. It's easier if you, once again, are better with just straight calculations, just to do this one because there's less uncertainty involved. If you feel confident in your conceptual understanding, then by all means, use this method because it's going to go a lot faster. I don't care which one you do, but you need to be confident in whichever one that you choose. So let's look at a new example. We have a 2 kilogram block held at rest, hanging from a string, so that's this block here, that's connected to a 3 kilogram block sitting on a surface with a coefficient of kinetic friction of 0.4. The string has been placed over a massless, frictionless pulley, that is this here. If the hanging block is now released, how quickly does the system accelerate? So, a couple things. First off, okay, what's a pulley? A pulley is simply usually something with a little wheel on it that just changes the direction of a force. So in this situation, the block is pulling down, but on the 3 kilogram block, so if this one's going down, this 3 kilogram is being pulled to the right, but it's the same force here, it's just being redirected in a different direction. It's not going to change the size of the force as long as the pulley is massless. So by massless, we mean that it is not very hard to get it moving, it doesn't have much inertia, and it's frictionless, meaning that we're not going to lose energy there to friction. Now, is that realistic? No, but any pulley that we're going to be dealing with, we can pretty much treat as being massless and frictionless, at least for right now. So let's first solve this using the system of equations method. I once again redrew the picture, and I went ahead and drew my FBD for block A. So I've got gravity going down, normal force going up, tension going to the right, which has to be bigger than the friction to the left in order for it to accelerate. And I wrote my two net force equations in the X and in the Y. It accelerates in the X, does not accelerate in the Y. As for block 2, or block B accelerates downward, so FGB must be bigger than the tension force going up. And we know there's no forces in the X, nice and easy. And in the Y, it must be accelerating downward. So let's go ahead and define, once again, our direction of acceleration as being positive. And this is really what people freak out a little bit. Remember, this acceleration here is the same as this acceleration because they are connected. Block B, I'm going to define positive as being down. And for block A, I'm going to define positive as being to the right. That's totally fine. The pulley just redirected the direction of that force. Additionally, I'm going to go ahead and rewrite some of these forces as positives and negatives. So, for my block B, tension is negative because it's upwards. I'm going to make that negative. For block A, friction is negative because that's going backwards. I'm going to go ahead and say that gravity is -2. And I start solving for things I know. I can easily find the gravitational force for each block because it's just their mass times 10. I can find the normal force for block A, because it's on a flat surface, so it's going to equal the gravitational force. There is no normal force for block B. And I could find the friction force on block A by just multiplying the coefficient by the normal force and getting 12 newtons. And now I'm going to rewrite my system of equations. So I have the two equations where it's accelerating. I have them here. And let's go ahead and combine them. And when we combine them, the tension forces go away. I'm left with FGB minus FF is equal to the mass of A plus the mass of B, all times the acceleration of the system. I rearrange it, I plug some numbers in, and we get that the acceleration of the system is 1.6 meters per second squared. Now the direction would be different for each block. For block A, it's going to be 1.6 meters per second squared to the right. For block B, it's going to be 1.6 meters per second squared down. Remember, for the system of equations method, really easy to double check our work. So we got that the acceleration was 1.6 meters per second squared, and I went ahead and rewrote my two net force equations without the changed positives and negatives. And I go ahead and rearrange them to solve for F10. We get that for block A, the tension force is 16.8 newtons. For block B, the tension force is -16.8 newtons. Perfect. They make a net force pair. And additionally, for block A, the tension force is greater than the friction force. And for block B, the gravitational force is greater than the tension force. So those both make conceptual sense that block A will accelerate to the right and block B will accelerate down. One final point is also that the acceleration we found is less than gravity. So in other words, if I just dropped block B without being attached to anything, it would fall at 10 meters per second squared, but it should be less now because block A is literally forcing it to move slower. It's dragging it back. Well, that was one way to solve this problem using the system of equations method, but can we also use Newton's second law for systems and get the exact same answer? And this might be the way you prefer to go. Well, of course, yes. I go ahead and I redraw my system and I drew out a system schema, and I drew out the FBDs once again for each block. And immediately I need to identify, okay, what are internal and external forces? Well, the only objects I care about are block A and block B, so the internal force, the force of tension in the string, don't care about that. I only care about the external forces, which is the normal force and friction force on block A, and the gravitational force, and the gravitational force on block B. Go ahead and calculate some of those. Same answers as last time. I use Newton's second law for systems. So the acceleration of the system is the net force external on the system divided by the mass of the system. And I see that FGA plus FGB plus FN plus FF, those are all my external forces. And I have MA plus MB on the bottom. But what we have to remember is that if we look, the gravitational force on A and the normal force, those are going to cancel. So I'm left only with FGB plus FF over MA plus MB. Stick in my numbers, get the exact same answer of 1.6 meters per second squared. Perfect, we're good to go. So what are the main takeaways for this lesson, this final lesson of the unit, analyzing connected objects? 1, can we compare the magnitude and direction of the acceleration of objects that are connected to one another? 1, the magnitude of their acceleration should be the same, but 2, their direction could be different if we have a pulley involved. 2, can we use a system of equations to determine the various unknown factors in a situation that involves connected objects? And additionally, 3, can we use Newton's second law for systems to do the exact same thing? Remember, I don't care which approach you use, but you want to be confident that you can do it all correctly.